Let's do one more section, the momentum equation. Consider a particle moving with a velocity v. Let its mass be delta m. This momentum would be delta m times v. Then, by Newton's second law, the net force delta F on this particle is nothing but the rate of change of momentum delta mv with time, d by dt delta mv. Let's take the torque of the force by cross multiplying vectorially at the left. So this gives you delta torque, delta t vector as r cross delta f. And that would be r cross d by dt of d delta m v. Now if we take a derivative of r cross delta m v, by chain rule we get delta dr by dt into delta m v plus r cross del by del t delta m v. Now this is nothing but velocity. Time derivative of the position vector r is nothing but velocity. So this term is like v cross v, cross product of two collinear vectors v and v. So this is 0. So r cross dt by d by dt of delta mv can be replaced by d by dt of r cross delta mv. And if we do this, we get delta t is equal to d by dt of r cross delta mv. This is the moment of momentum. R cross delta mv is the moment of momentum. We integrate this and we say the total torque acting on a body is the time rate of change of the moment of momentum. This is the moment of momentum equation for a particle. For a control volume formulation, the Reynolds transport theorem with the specific value of the moment of momentum h is equal to r cross v, that is the moment of momentum per unit mass, then dh by dt is obtained in terms of the rate of accumulation and the net efflux of momentum. So we get the equation for a controlled volume as T is equal to delta H by delta T, which is the rate of accumulation of momentum within the controlled volume, plus the net efflux of momentum across the controlled surface at the inlet and outlet. We again would use the same sign conventions as we use for momentum. We apply this law to a very simple example. Consider a lawn sprinkler. It consists of two arms rotating about a central pivot, a frictionless pivot. There's water coming out at 60 degrees to the edge, and because of this water coming out, the arm rotates. We have to determine that if there is no friction, what is the rate at which the arm rotates. The equilibrium rate of rotation would be obtained when the net torque acting on these sprinkler arms would be 0. So we have to use the momentum equation to determine what should be the angular rate of rotation of these arms so that there is no net torque acting on this sprinkler. For this, we consider a control volume. We take a stationary control volume enclosing the entire region swept by the arm as shown. The frame of reference is inertial because the frame is not rotating. As the arm rotates, the water issues in different directions at different times, and so the linear momentum flux changes with time. The flux of momentum has a constant direction along the axis of rotation and magnitude. Thus, it is more convenient to work with the z component of the momentum equation rather than with the momentum equation. Although the flow within the control valve is unsteady, the total momentum within the control valve is constant with time. This is because R cross V for any segment of the arm of the sprinkler is independent of the angular position of the arm. Whatever angular position, the value of R cross V is the same. And so, angular momentum does not change with time. Rate of accumulation is 0. The rate of accumulation is 0. The net torque we want is 0. So, the sprinkler arms would rotate at such a speed that the net efflux is 0. Net efflux or momentum is 0. Now, the two orifices at 1 and 2, at both the sign of the momentum is the same. The sum should be 0. Each has the same value. So, it means the moment of momentum of flux at any orifice is equal to 0. The symmetry requires the fluxes from the two orifices to be equal. The efflux of momentum at each of the two jet orifices must vanish. This is possible only if the velocity of the water coming out of the jet is in the radial direction. Only if the momentum is in the radial direction would R cross momentum be 0, or momentum would be 0. So, in the frame of reference that we have, the velocity should be coming out, the water should be coming out radially. How we do this? This is V jet relative with respect to the sprinkler arms at 60 degrees to the vertical. But the jet arm is rotating and it has a component omega r downwards if this is moving downwards. So, the net velocity, the effective velocity is this, the difference of these. If this is to be radial, then the omega r should be equal to the vertical component of the relative velocity of the jet. The tangential component of the absolute velocity is V jet relative cosine 30 degrees minus omega r, or omega should be V jet relative sine 30 degrees divided by r. So, we know the V jet velocity relative at what rate it is coming out. That we can determine by applying the Bernoulli equation from the pressure at which the water is being supplied to the sprinkler. We can calculate the relative velocity of the jet, and then we can find out what would be the rate of rotation of the sprinkler if it is frictionless. Thank you very much.